We can all agree that Iron Man's suit is very impressive. It can do lots of cool things, like fly and shoot these energy blast thingies. But just how much power does this whole thing consume? Well, in Iron Man 1, Tony Stark himself says that his chest reactor can produce 3 gigajoules of energy per second. This value is just the power of the suit in disguise, and translates to 3 gigawatts of power. That sounds like a lot of power, but how does it compare? Well, it's about twice the power output of Machamp and Magcargo, Pokemon that I covered in a different video, but it's not in the 5 largest power facilities in the world. In fact, it isn't even in the top 20. So what I'm saying is that Marvel might have actually done their fact-checking on this one. But I digress. Iron Man's reactor is a fusion reactor, meaning it combines lighter particles together to make heavier ones, releasing energy in the process. The most common fusion chain is the proton-proton fusion chain, which begins by fusing 2 protons into a particle called deuterium, releasing energy in the form of a neutrino and a positron. This is combined with another proton to make helium-3, releasing energy in the form of a gamma ray. Then finally, we bring in another helium-3 to make a helium nucleus and 2 protons. Now this chain is very common in young stars like our Sun, and is the kind of chain we're looking to replicate on Earth. Now, in theory, fusing elements all the way up to iron releases energy. In order to get energy out of the heavier elements, we would actually need to split them up through fission, which is the opposite of fusion. Okay, but why does this happen, and what makes iron so special? Well, to explain that, we need to talk about binding energy. This is a graph of the binding energy of a nucleus per nucleon, which is a word that describes either a proton or a neutron. What this graph tells you, essentially, is how much energy goes into keeping all those protons and neutrons stuck together, with iron here at the top being the most stable element. Now, since mass and energy are the same thing, if more energy goes into keeping the protons and neutrons stuck together, they will each weigh a little less. To visualize, that means that 2 protons will actually weigh more than a deuterium atom, even though they both contain 2 nucleons. Now, the observant of you might have noticed that the left side contains 2 protons, and the right side contains 2 protons and a neutron. While a proton and a neutron don't have exactly the same mass, it is very similar, and this mass difference here is due to the difference in binding energy. As we work our way up the chain, the same thing happens. A helium-3 weighs less than a deuterium atom and a proton, and finally a helium nucleus and 2 protons weigh less than 2 helium-3 atoms, though this one is a little less obvious, and you'd have to actually go through the math to convince yourself. Fission works on the same principle, except instead of combining, we split up heavy elements to make them weigh less. Okay, so now we understand how fusion works in the Sun, which keeps everything on Earth alive via this method. However, fusion is a very difficult process to get going. This is because, firstly, we need extremely high temperatures to create a plasma where electrons and protons exist separately. After that, we are left with 2 protons to fuse, both of which are positively charged. Now we know that same charges repel each other, so we need some outside pressure to push them together. This repulsive force is given by Coulomb's law, where Q are the strengths of the 2 charges, 4 pi epsilon naught are some constants, and d is the distance between the charges. Now, since this distance d is on the bottom, that means the closer the charges get to each other, the more pressure we will need to keep them there. And we want these protons to get very, very close, meaning we're going to need a lot of pressure. Now, our good friend the Sun has this easy. The ongoing fusion keeps it really hot, and its mass weight creates enormous pressure in the center just through gravity. On Earth, however, this is much harder to achieve because of the massive energy costs that need to go in to get the process started. And often then, the energy we get out is much smaller than the energy we put in. The largest fusion reactor on Earth is ITER, which stands for International Thermonuclear Experimental Reactor. ITER is just an experiment with many goals, but their second goal is to generate 500 megawatts of fusion power in its plasma. 500 megawatts is much less than the 300 gigawatts Iron Man produces, and ITER will weigh a whopping 23,000 tons, be built on a 42-hectare platform, the equivalent of 60 football fields, have a height of 73 meters and a plasma volume of 840 meters cubed. That's 840,000 liters. That is a fair bit bigger than Tony Stark's tiny heart-sized reactor. On top of this, ITER will also use 100,000 kilometers of superconducting wire as magnets to contain the plasma inside the reactor, and will be surrounded by a vacuum to protect the outside world from the plasma, which will be running at a whopping 150 million degrees Celsius. So Tony Stark's reactor must be pretty technologically advanced. But hold on a second, rewind. Why do we need magnets if we're just smashing particles together and combining them? And how on earth would 100,000 kilometers of wire even make a magnet? Well, in order to explain that, we need to talk about what an electromagnet is. An electromagnet is created very simply, with just a wire. If we connect this wire to a battery, a current will flow throughout the wire. Now, Ampere's law tells us that a magnetic field must be created around the wire. But this magnetic field isn't very useful, it just kind of wraps around the wire. So what we do is we wrap the wire into a coil shape. Then all the magnetic field lines point in the same direction, and we have a magnetic field that can be turned on and off with the press of a button. Electromagnets are widely used throughout society and in loads of devices, from speakers and headphones to those industrial magnets used to lift cars and scrap metal. Okay, so now we know how copper wire can make a magnet, but what does that have to do with fusion? Well, as we mentioned before, the plasma used in fusion is insanely hot. This means if it comes into contact with anything else, such as the walls of our reactor, it would not only instantly lose its heat, but also probably damage the reactor walls. But in order to stop the plasma touching the walls, we would need some way of containing the plasma without touching it, some kind of dark magic to hold it in place. Or as we call it in physics, the Lorentz force, the value of which is given by this equation. Now E represents the electric field, which we have none of, so our equation simplifies to this. Here, Q is a scalar that gives the strength of the electric charge, V is a vector of the speed of the charge, and B is a vector describing the magnetic field. The X in between our two vectors describes a cross product, a way of multiplying vectors that means the resulting force will always be perpendicular to both V and B. This means by using a magnetic field perpendicular to the motion of the charge, in this case the circles with dots mean the magnetic field is pointing out of the screen towards you. If we do this, we can confine charged particles to a circular path without having to touch them at all. Therefore, we have a way to stop our ultra-hot plasma from touching anything and to keep our reactor running. So, now you have a good idea of how Iron Man generates these 3 gigawatts of power, but what can he do with them? Well, firstly, Iron Man does a lot of flying, which must require energy. In a simplified case, we can work out how high Iron Man will be able to fly by just considering his gravitational potential energy, which is equal to mass times the gravitational constant times height. Power is energy over time, and upwards velocity is height over time, giving us this equation for upward velocity. From the Marvel Wiki, we see the weight of Tony Stark in his suit is 425 pounds, more helpfully written as 192 kilograms. We know Earth's gravitational constant g is 9.8 newtons per kilogram, so putting it all together gives us an answer of about 1,600 kilometers per second. In other words, Tony Stark would be able to fly to the top of Mount Everest in just 5.5 milliseconds. That's insane, but this calculation doesn't come without its quite serious limitations, namely no air resistance, which is definitely not the case. We've also assumed the suit can convert produced energy into gravitational energy without any losses, again unlikely to be true, and have restricted Iron Man to flying only upwards. On top of this, we haven't considered if there would be enough hydrogen in the reactor to make this trip. 5.5 milliseconds doesn't seem like a lot, but at maximum power, that's 16.5 megajoules of energy, the equivalent of 6,700 Big Macs. Thankfully, Stark doesn't have to eat all these Big Macs because we're making energy by fusion, which uses protons instead of Mackies. What's more, we can actually work out how many of these we'd need to get up Mount Everest. Remember that energy generated is based off the difference in mass between what we begin with and what we end with. Looking at our fusion chain, we see a total of 6 hydrogens as input, and a helium, 2 hydrogens, and 2 positrons as output. Gamma rays and neutrinos are massless, so they can be ignored. We can visualize this on our scales like so. Now, we're looking for the mass difference, so the first thing we notice is that both sides have 2 extra hydrogen atoms, which we can just get rid of. Then, on the right side, we have 2 positrons, which are just anti-electrons. Upon creation, they will annihilate with 2 regular electrons, creating energy in the process. So, we actually have 2 electrons and 4 protons transformed into a helium nucleus. We add up the masses for each side, then find the difference between them, and finish with the well-known formula E equals mc squared to find that this reaction releases only 4 picojoules of energy. But don't forget, this is the energy released by only 4 protons and 2 electrons, which don't weigh a lot. Dividing the energy released by the mass shows us that this fusion chain releases 640 terajoules of energy per kilogram. That means that the journey up to Mount Everest would only use 26 micrograms of fuel, or essentially nothing. Running at full power, the reactor would only consume about 5 milligrams of fuel per second, equivalent to 17 grams per hour. That's a fair bit more efficient than your average car. So flying is no problem for the little reactor, but what about the projectiles that the suit emits? Well, we are told in the original Iron Man that they are some kind of repulsor technology. The comics go into even more detail, specifying that these are repulsors based on some kind of advanced plasma projectors. Now, the interesting part about this quote is that they claim it can generate a force equal to 150 pounds of TNT. This is a bit of a difficult statement to digest, because TNT is not a unit of force, but of energy. 150 pounds of TNT would make a cube with 35 centimeter sides and contain 285 megajoules of energy. With a power generation of 3 gigawatts, Iron Man could fire this beam 10 times per second, with a bit of energy left over for flight, more than enough for combat. To put this into perspective, a 1-ton car moving at highway speeds of 130 kilometers an hour has 652 kilojoules of energy in it. That means that an Iron Man blast has the energy of over 400 motorway car crashes. Wearing your seatbelt could save your life in a car crash, but it won't save you here, and these blasts would likely be fatal to humans and damaging to other superheroes. But unlike other characters I've covered, Marvel seems to have actually checked some numbers on this one. Despite all of that, Iron Man is still a force to be reckoned with, and definitely someone you want to be fighting with instead of against. I'm just glad he's not real. Now that would be terrifying.